In this presentation, I'll go through some notes from Chapter 6 of the book, Designing Data-Intensive Applications. Chapter 6 is called Partitioning. So here are the topics in 6th chapter. The first is partitioning and replication. The second is partitioning by key value data. And we'll look at partitioning by key range, by hash of key, and skewed workloads and relieving hotspots. In the third topic, we'll look at partitioning and secondary indexes, and we'll cover partitioning secondary indexes by document, partitioning secondary indexes by term. Then we'll look at rebalancing partitions, and we'll look at strategy for rebalancing and operations, whether to do the rebalancing automatic or manual rebalancing. And the last topic is request routing, and we'll look at parallel query execution. So here is the cool diagram of chapter 6. You can pause the video and appreciate the image as much as you can. So let's look at partitioning and replication. Partitioning is usually combined with replication so that the copies of each partition are stored on multiple nodes. This means that even though each record belongs to exactly one partition, it may be stored on several different nodes for fault tolerance. Everything we discussed in chapter 5 about replication of databases applies equally to replication of partitions. The choice of partitioning scheme is mostly independent of the choice of replication scheme. So here we look at combining replication and partitioning. Each node acts as a leader for some partitions and follower for other partitions. A node may have more than one partition. If a leader-follower replication model is used, the combination of partitioning and replication looks like the image over here. Each partitioning leader is assigned to one node and its followers are assigned to other nodes. Each node may be the leader for some partitions and a follower for other partitions. Partitioning of key value data. Say you have a large amount of data and you want to partition it. How do you decide which records to store on which nodes? Our goal with partitioning is to spread the data and query load evenly across nodes. If every node takes a fair share, then in theory, 10 nodes should be able to handle 10 times as much data and 10 times the read and write throughput of a single node, ignoring replication for now. If the partitioning is unfair, so that some partitions have more data or queries than others, we call it skewed. The presence of skew makes partitioning much less effective. In an extreme case, all the load could end up on one partition, so 9 out of nodes are idle, and your bottleneck is the single busy node. A partition with disproportionately high load is called a hotspot. Partitioning of key value data. Partitioning by key range. One way of partitioning is to assign a contiguous range of keys from some minimum to some maximum to each partition. The partition boundaries might be chosen manually by an administrator, or the database can choose them automatically. This partitioning strategy is used by Bigtable, its open source equivalent HBase, RethinkDB, and MongoDB before version 2.4. However, the downside of key range partitioning is that the certain access patterns can lead to hotspots. If the key is a timestamp, then the partitions corresponds to a range of time. Example, 1 partition per day. Unfortunately, because we write data from the sensors to the database as the measurement happens, all the writes end up going to the same partition, the one for the day. So the partition can be overloaded with writes while the others sit idle. So continuing on the partitioning of key value data, partitioning by hash of key. So this is another strategy. Because of the risk of skew and hotspots, many distributed data stores use a hash function to determine the partition of a given key. A good hash function takes skewed data and makes it uniformly distributed. Say you have a 32-bit hash function that takes a string. Whenever you give it a new string, it returns a seemingly random number between 0 and 2 to the power of 32 minus 1. Even if the input strings are very similar, their hashes are evenly distributed across a range of numbers. Unfortunately, however, by using the hash of the key for partitioning, we lose a nice property of key range partitioning, that is the ability to do efficient range queries. Keys that were once adjacent are now scattered across all partitions, so their sort order is lost. Skewed word loads and relieving hotspots. As discussed, hashing a key to determine its partition can help reduce hotspots. However, it can't avoid them entirely. In the extreme case where all reads and writes are for the same key, you still end up with all the requests being routed to the same partition. This kind of workload is perhaps unusual but not unheard of. For example, on a social media site, a celebrity user with millions of followers may cause a storm of activity when they do something. This event can result in a large volume of writes to the same key. Hashing the key doesn't help, as the hash of the two identical IDs is still the same. Today, most data systems are not able to automatically compensate for such a highly skewed workload. So it's the responsibility of the application to reduce the skew. For example, one key is known to be very hard. A simple technique is to add a random number to the beginning or the end of the key. Just a 2-digit decimal random number would split the writes to the key evenly across 100 different keys, allowing those keys to be distributed to different partitions. A secondary index usually, so here we are talking about the partitioning and secondary indexes. A secondary index usually doesn't identify a record uniquely, but rather is a way for searching of occurrences of a particular value. Say, find all the actions by user 123. Find all the articles containing the hogwash. Find all the cars whose color is red, and so on. Secondary indexes are the bread and butter of relational databases. They are common in document databases too. Many key value stores, such as HBase and Voldemort, have avoided secondary indexes because of their added implementation complexity. But some, such as RAG, have started adding them because they are so useful for data modeling. And finally, secondary indexes are the raison d'etre of search servers such as Solr and Elasticsearch. The problem with secondary indexes is that they don't map neatly to partitions. There are two main approaches to partitioning a database with secondary indexes: document-based partitioning and the term-based partitioning. Let's look at the document-based partitioning. So as the cartoon shows, the partitioning secondary indexes by document. So in this indexing approach, each partition is completely separate. Each partition maintains its own secondary indexes, covering only the documents in that partition. It doesn't care what data is stored in other partitions. Whenever you need to write to databases, to add, to remove, or to update a document, you only need to deal with the partitions that contains the document ID that you're writing. For that reason, a document partition index is also known as local index as opposed to a global index. Partitioning secondary indexes by term. So this cartoon shows the partitioning secondary indexes by term. And here, rather than each partition having its own secondary index, that is a local index, we can construct a global index that covers the data in all partitions. However, we can't just store that index on one node, since it would likely become the bottleneck and defeat the purpose of partitioning. A global index must also be partitioned, but it can be partitioned differently from the primary key index. We call this kind of index term partitioned, because the term we are using or we are looking for determines the partition of the index. Here, a term would be color red. For example, the name term comes from the full text indexes, a particular kind of secondary index where the terms are all the words that occur in a document. The advantage of global, that is term-based index over a document-based index, is that it can make reads more efficient. Rather than doing scatter-gather all over partitions, a client only needs to make a request to the partition containing the term that it wants. However, the downside of global index is that the writes are slower and more complicated, because a write to a single document may now affect multiple partitions of the index. Every term in the document might be on the different partition or a different node. In an ideal world, the index would always be up to date, but every document written to the database would immediately be reflected in the index. However, in a term-based index, that would require a distributed transaction across all partitions affected by a write, which is not supported in all databases. In practice, updates to global secondary index are often asynchronous. That is, if you read the index shortly after a write, the changes that you may just have made may not be reflected in the index. For example, Amazon DynamoDB states that its global secondary indexes are updated within a fraction of a second in normal circumstances, but may experience longer propagation delays in case of faults in the infrastructure. Rebalancing partitions. Over time, things change in a database. The query throughput may increase, so you may want to add more CPUs to handle the load. The dataset size increases, so you want to add more disks and RAMs to store it. A machine fails, another machine needs to take over failed machine's responsibilities. No matter which partitioning scheme is used, rebalancing is usually expected to meet some minimum requirements. For example, after rebalancing, the load, that is data storage, read-write request, should be shared fairly between the nodes in the cluster. While rebalancing is happening, the database should continue accepting read and writes. No more data than necessary should be moved between nodes to make rebalancing fast and to minimize the network and disk IO read and disk IO load. Fortunately, there is a fairly simple solution. Create many partitions than there are nodes and assign several partitions to each node. For example, a database running on a cluster of 10 nodes may split into 1,000 partitions from the outset so that approximately 100 partitions are assigned to each node. Now, if a node is added to the cluster, the new node can steal a few partitions from every existing node until the partitions are fairly distributed once again. So this cartoon shows adding a new node to the database cluster with multiple partitions per node and how the rebalancing happens when a new node is added to the system. Now, let's talk about dynamic partitions. For databases that use key range partitioning, a fixed number of partitions with fixed boundaries would be very inconvenient. If you got the boundaries wrong, you could end up with all of the data in one partition and all of the other partitions empty. Reconfiguring the partition boundaries manually would be very tedious. For that reason, a key range databases such as HBase, RethinkDB create partitions dynamically when a partition grows to exceed a configured size. On HBase, the default size is 10 gigabytes. It is split into two partitions so that approximately half the data ends up on each side of the split. Conversely, if lots of data is deleted and a partition shrinks below some threshold, it can be merged with an adjacent partition. This process is similar to what happens at the top level of a B tree. An advantage of dynamic partition is that the number of partitions adapts to the total data volume. If there is only a small amount of data, a small number of partitions is sufficient. So overheads are small. If there is a huge amount of data, the size of each individual partition is limited to the configurable maximum. Now, whether to choose automatic or manual rebalancing. There is one important question with regard to rebalancing that we glossed over. Does the rebalancing happen automatically or manually? There is a gradient between fully automatic rebalancing, that is, the system decides automatically when to move the partition from one node to another without any administrator interaction, and fully manual. Fully automated rebalancing can be convenient because there is a less operational work to do for the normal maintenance. However, it can be unpredictable. Rebalancing is an expensive operation because it requires rerouting requests and moving a large amount of data from one node to another. If it is not done carefully, this process can overload the network or the nodes and harm the performance of other requests while the rebalancing is in progress. Such automation can be dangerous in combination with automatic failure detection. On a high level, there are quite a few different approaches to request routing problem. Allow clients to contact any node via round robin or load balancer. If that node coincidentally owns the partition to which the request applies, it can handle the request directly. Otherwise, it forwards the request to an appropriate node, receives the reply, and passes the reply along to the client. Send all the requests from clients to a routing layer first, which determines the node that should handle each request and forwards it accordingly. This routing tier does not itself handle any request. It only acts as a partition-aware load balancer. The third is require that clients be aware of partitioning and the assignment of partitions to nodes. In this case, a client can connect directly to the appropriate node without any intermediary. So in this cartoon, we can see three different ways of routing a request to the right node. The first, the client chooses node 0 randomly, and then node 0 forwards the request to the appropriate node which contains the partition. The second diagram, we see the client connects to the routing tier, and the routing layer forwards the request to the appropriate node which contains the partition. The third one, the client is partition aware, so it directly connects to the node 2 which contains the appropriate partition. The other alternative is using Zookeeper to keep track of assignment of partitions to nodes. So here, client contacts a routing tier goes to node 2. Routing tier has information from Zookeeper as to which node to connect to, which has the appropriate partitions. So this concludes chapter 6 notes. Hope this was useful. Have a nice time. Like and subscribe for more such content.